Alright, this is the demo and evaluation video for the recursive listing strategy for type-directed identifier listing. We'll jump right in and we'll fill in this case for erase bar just like we've done before. Pick out 0, and here we'll pick out successor, pick out erase var, and it will determine that we couldn't paste this back in without getting an incomplete term error, so we'll immediately be asked for more information. Next, of course, is erasing full simply typed lambda calculus terms back down to raw terms. So we'll fill this in with the var case and we'll use erase var, and again we have to give it more information before it pastes the term in. Fill in the parameter x and then it is complete and paste the term in. Here we're going to do app and we're going to erase the function side, app again, erase the parameter side, and finally we will do the lambda side. We can fill in type without a problem, and we want to erase the body. We have to give the body immediately. Right, so we can move on to the soundness proof. Recursively call sound on X and sound on X again. No issues there. So now we'll move on to function comparison. In the case where both the input and output types are equal, well then the whole function is equal. It's not a problem. Here, clearly they're not equal. And why are they not equal? Well, the target is incompatible, and it's incompatible for the reason passed in. And here they're again not equal, and they're not equal because the source is not compatible, which again we're given the reason for. And of course here have STLC equal. Here it's not equal. And why is it not equal? Well, if we look for reasons things aren't equal, there's only one that we're allowed to put in there. Again, it's not equal, and there's the other reason. And here we say that it's not equal, or sorry, we say that we want to call compare fun and compare STLC. And here, this is something that the recursive case doesn't help with. We still have to manually fill in these terms because this is a case of a meta variable getting into the type, not the type being incomplete. So we can reload that. We can again call compare STLC recursively, and we're told what terms to put in here. So this is our predicate. It does not catch this sort of thing. It only was written to catch incomplete terms. So we don't handle that failure mode yet. So this isn't perfect, but it does handle a big failure mode. So now we have a whole string of data types, and we'll get to this check app case. Here it's not well typed because it's not a function, and here it actually is well typed, and this is the other one that it doesn't handle, where this doesn't actually refine because of that issue with actually applying a function to metavariables in the type will mean it doesn't even show up in the refinement list. So this is another focus for future work. So we'll get rid of that and say we'll try that out, and again it'll show off the error that we're talking about, so you can see that we're applying a function to a metavariable, and that can't unify with a particular output case for the function, of course. So we'll fill in the term that we want here, which is tapp of tr and z. When we reload, we get a REPL back, which means Idris successfully loaded the function. Here, this is not well typed, and it's not well typed because the argument type doesn't match the function type, and we'll fill in the reason for the mismatch and go on our way. Here it doesn't work out because the argument is bad. So no, it doesn't work out because the argument is bad, and the argument is bad for the reason given in the typing decision on the argument. Here, the function is bad, and so why is it bad? Well, it's bad again for the reason given here. And finally, in this case, we'll just pick a thing to report and say that the argument is bad. And when we go here, of course, it won't let us use the function's reason for being bad. We have to use the argument's reason for being bad, since that's the one that we said we're reporting. Alright, so here, again, we'll run into this. If we want to look up well-scoped, yes, we can't, so we'll have to just build the whole term ourselves, which will be well-scoped yes, successor of x. And of course, this is a constructor for typed de Bruijn indices, and natural numbers are untyped de Bruijn indices. In this case, of course, this will work out just fine. We can say no, and, well, why not? We'll build up the successor of the reason that we're given. And now we can move on to look up var, where it's not well scoped, and we'll use that base case reason that is typed exactly for this context of looking up a natural number in the null context. Here we have a 0, so again we'd like to say yes, but that doesn't occur in the menu, so we have to build up the term by ourselves, which is just yes 0, and reload, and finally if we want to build this term, we can call lookup successor on lookup var, and again we have meta variables in our type. So this is probably the next thing that needs to be addressed, is this issue of variables in the types, and perhaps even some sort of smart term construction of here we have a type with some meta variables occurring in it, and here we have the values that those meta variables should be filled into. So if we just fill in the meta variables with those values, the whole thing will go through, and it would be nice for it to build that term for us. So in any case, we'll make this window go away and reload. And we're just about home free. Again, we can't build up the term there because of functions applied to meta variables in the type. So we're going to instead say that this is if we have a typing decision that gives us back a type De Bruijn index for some variable, we can just build a type variable term from that. On the other hand, if it's not in scope, then the reason it's not well typed is that the variable is out of scope, and there's the descriptor of how far you go before you get out of scope. And if we have a well-typed lambda term, we're going to fill in something over here as we've done before, because we'll need that A in scope. But again, we can't put in well-typed yes. We're going to put in well-typed yes directly of tlam. A is the type and term is the well-typed term, and reload. And here, of course, we can say no, it's not well typed because the body's not well typed. And why is the body not well typed? That's the reason. And finally, we can write our dispatch function, which is check var of lookup var, and again we have meta variables in our type that we can make those go away very nicely, quickly, and easily. Reload. Once again, we'll do of course in this case we'll do check app, and again we're going to wind up with meta variables in our type and be told what things they need to unify with. Check X in context, and again check Y in context, and reload. And finally, check the lambda, and we're going to hit this issue of meta variables one more time. We're actually given an expression here that we want to build up. And if we try to reload again, we're told what to fill in here. And if we reload one more time, we have the REPL back, and we're done. So once more, we're going to save the events buffer. Having saved the events buffer, that concludes the demo and evaluation.